Hello and welcome to this project in Unit 2 Multivariate Calculus presented by EduOnix. Today we are going to be doing a gradient visualization with matplotlib. So let's go ahead and dive right in. So first things first, I'm going to open up my terminal command prompt. Again, I'm working in Windows 10. And then I'm going to CD over into the directory that I want to start my Jupyter Notebook in. Just like the other projects, I'm using a Jupyter Notebook today. Even more specifically, I'm actually going to use Jupyter Lab because I like the functionality that it provides. And so if you have Jupyter, you can follow along directly with me, but any Python programming IDE would actually work. So to start this up, I'm just going to type Jupyter Lab. This is going to open up a page in my browser, specifically on the local host, usually port 8888 actually. And so here we go. This opened up. In this directory, I have the other couple of projects that we've done up into this point. I'm just going to start a new Python default notebook. I'm in Python 2.7, but we will verify that in a second. And then I'm good to go. I'm good to start programming right here. Control B will minimize that directory on the side. So let's dive right in. First things first, we need to import what we need. I'll import the system so we can print our Python version number. We're going to use NumPy and using the namespace np. We're also going to use matplotlib.pyplot as PLT. But actually before this, I'm just going to import matplotlib as matplotlib as well. So we have those. As always, I like to print out the version numbers so that we can verify that all of these were installed correctly, as well as just see if we're on the same page here. In all likelihood, these don't have to be exact. However, if you do run into errors and are using different versions of these different libraries, that could be a source of the error. So we have NumPy, and we also have matplotlib is our last one. And again, the dot format, we're substituting a variable into a string and then printing it out. All right, so Shift-Enter, we'll go ahead and run this cell. And these should all import correctly, and we'll be good to go when that happens. So it takes a second, but there we go. Again, Python 2.7 on a Windows 10 machine, NumPy 1.14, and Matplotlib 2.1. All right, so first things first, we are going to do a gradient visualization, and what we need to do this is a mesh grid of X and Y points. So the mesh grid is going to be a large two-dimensional array that we're going to use for our plots, and it's going to let us define a function to plot as well. So let's go ahead and do that. We want to generate 2D mesh grid. So we're going to start. And this n of x and n of y is going to be like a quality control. It's how many points we want in the x and the y direction, so number of points. And then what we can actually do is do an np.linspace. So from 0, I'm going to go to 10 with those 100 points. So this will give us a point every tenth of 1, or so 1/10. We'll have a point. So 100 points from 0 to 10. So that's x. We can do the same thing for y. Linspace 0, 10 will give us a nice square graph here, number y. And then making a mesh grid out of this with NumPy is really straightforward. We have x of v, and y of v is going to be the np.meshgrid. And what we're going to do is simply combine this x and this y. So let's go ahead and run that, and that goes really quickly. If we print one of these out, we see we have a large array starting at 0 going to 10. This isn't including all of the numbers here. We got some dots, but in general, we have that large matrix. We should have a shape here of 100 by 100, so yep, we should be good to go. All right, Next, we need to define a function to plot. So to do that, actually, let me clear these outputs really quick. To do that, we're going to use a Python function, which is definition. We're going to define our own function. We're going to call this f of x and y. So it's going to take two input variables, x and y. And what it's going to do is it's going to return x times y squared. That's the function I'm going to be doing today, x times y squared. Now this is going to match the plot that we generated or we viewed in the lecture on gradients. Feel free to do your own function if you so desire. Don't make it too complicated because we're going to later in this project calculate the partial derivatives ourselves. So you don't want to give yourself too much work, but feel free to do whatever you like. All right, next we're going to calculate the z value for each xy point. So the z value is going to be the result of this function. So we're just simply going to call z equals f times x of v and y of v. X of v and y of v are going to be every point in our mesh grid. It's going to calculate the z value for. Let's just go ahead and run this, and we should be good to go there. If we print out our z, we see we have a similar array now. Should have an x and a y point for each, or this is the z value. We have the shape should be 100 by 100, and indeed it is. All right, so now we can move on to plotting this. We're going to be using a color plot in matplotlib. There's our outputs. So we want to make a color plot to display the data. And we haven't calculated the gradients yet. We're going to display the data, and then we're going to calculate the gradients and add them onto it. So we're using matplotlib.pyplot as PLT, namespace PLT. So we're going to start with a figure. So we can define a figure size just to make this look nice. We're going to do 14 by 12. And then we add to this pyplot figure a p color plot. So it's just p color. So x points, y points, and then our z value for each. The z is going to determine the color. Let's add a title so we know what we're looking at. 2D. There we go. Color plots of f of xy equals xy squared. All right, there's a good title. Let's add a color bar to this. It's as easy as typing plt.colorbar. And then is a pyplot, so we have to call the show function at the end. Once we do, we can run that, and we should get a nice graph here. And indeed we do. So here's our color plot with our color bar on the right, going from 0 to 10 on both the x and the y axis. And this is the graph x times y squared. So as expected, we have really large values over here where x is 10 and y is 10. We have 1,000. In fact, all the way into the bottom left, we have 0. 0 times 0 squared is, of course, 0. So going from 0 to 1,000 along the diagonal. And we have 0 in the top left and top right points as well. All right, so there's our graph. Let's go ahead and move on to the gradients. We're going to calculate them with NumPy. One thing that we don't want to do, though, is calculate the gradient for every single one of these points. So what we're going to do is generate a new 2D mesh grid for the gradient. And so we're going to just make this smaller. So we're going to do only 10 points this time, so 10 by 10. So that way we can calculate the gradient at every integer value on this graph. So we got to do the same thing as we did before. We'll do an np linspace 0, 10, number of x, and then y is going to be equal to np.linspace 0, 10, number of y. And then you make the mesh grid from that. I'm going to call this x of g and y of g to delineate that is for the gradient equals np.meshgrid x and y. All right, that should give us the mesh grid. Now let's actually calculate the gradient. So calculate the gradient of f of xy. So one thing to note here is we're going to use the np.gradient function. And what we can actually do is just pass it the function that we defined above. So f of xg and yg. So it's going to calculate that z value at these x and y points, and then for that z value, it's going to calculate the gradients. So this is going to be g of y and g of x. And the important thing to note here is that since this is NumPy and it deals with arrays, it's going to return this in a rows first format. So rows then columns. But in the context of x and y, the rows would actually be the y and the column would be the x. So this is actually going to be backwards. It's going to spit out our y value first and then our x values for the gradient second. So that's an important thing to keep in mind. NumPy deals with rows first. And actually, the rows here is going to be the y. So just something to keep track of there. All right, so we've calculated our gradient at all of those points. Let's go ahead and add this back to our color plot. So what we can do is just go back up here. We already defined this color plot. Let's take this data and just Control Z and bring this on down here so we don't have to retype a lot of this out again. So we have our figure size, we have our color plot, we have a title, and let's change this title. We'll say gradient of x of y squared. And then what we're going to do is we're going to add a quiver plot. We're actually going to add this after the color bar. So plt.quiver. And so the quiver is going to take the x points, the y points, and then the x points of the gradient and the y point of the gradient. So we'll start with x of g, y of g. Those are our x and our y mesh grid for our gradient. Then we pass the x component of our gradient, the y component of our gradient, and then we're good to go. We can just add some formatting on here. So we want to scale this 1000, and then color, let's make them white so they stick out nicely. And we have our plt.show there, so we should be good to go. Let's go ahead and run a shift enter here and see how we do. Okay, so here comes this plot. Let me scroll down here. And here is our gradients. And this looks really nice. So we have the gradients pointing to the upper right, just as we expected, according to the function x equals y squared. So they're pointing up on the y direction more so than they're pointing to the right on the x, which makes sense because we have the exponential and the y here. Also, we talked about a little bit in the lecture how these gradients look along these x and these y axes. And you see here at x equals 0, it's pointing dramatically to the right. That is because the gradient or the partial derivative with respect to x is actually going to be y squared. So the x component is equal to y squared. The y of 10 here, 10 squared equals 100. So we have a strong gradient to the right here. Down here, not so much, because the gradient with respect to y is just going to be 2xy. So since we have 0 on the y, that gets equal to all 0. And we have a mix in between here with the gradients pointing up, increasing, again, the magnitude of the gradient denoted by the length of the vector, or the length of the arrow. So we have really large slopes up here in the top right, which makes sense. We're increasing exponentially, and basically 0 slope down here in the bottom left. So this is a really pretty graph. But how do we actually know that NumPy was calculating the gradients correctly? Well, what we want to do here is actually just go back and double check them ourselves. So what we can do is calculate the gradient of f of xy equals xy squared ourselves. And so what we're going to do is we're going to define two of the partial derivatives. So we're going to do the partial with respect to x and the partial with respect to y. So the first is going to be the partial, I'm going to call this ddx, partial with respect to x of xy, two inputs, x and y. And so if we look at our equation, x equals y squared, the partial with respect to x, we can just treat the y squared as a constant, and the derivative of x with respect to x is just 1. So what we get back is just y squared. So we want to return y squared. And you do the squared with this double asterisk in Python. So there's that. Now let's do our partial with respect to y. And what we want to return here So we have our equation. We hold the x constant. The partial derivative of y squared with respect to y is going to be 2y. So as a result, the partial here is going to be 2xy. So what we can return is 2 times x times y. So there's our partials. Now let's call these. So our x component of the gradient is going to be the partial with respect to x. So we can simply call ddx of x of g and y of g, which again is our mesh grid for our gradients, that 10 by 10 array. G of y is going to be equal to ddy of x of g and y of g. So there's those. So let's run this. Looks good. Everything calculated correctly. Let's go up here and grab this and bring it back down so we don't have to retype it. No reason to waste time here. And let's change this title. Instead of saying the gradient, let's just call this the plot of our partials here. So we'll call it y squared and 2xy. So this is the x component of the gradient, and this is the y component of the gradient. And down here we have our mesh grid, which is already defined. These g of x and these g of y we've redefined as our partials. Our scale stays the same. We also want it white. All right, let's see how we look. And indeed, as expected, we get back out the exact same thing as we did in the previous plot. So NumPy was, in fact, calculating these partials correct, since we went back and verified the partials ourselves, both with respect to x and with respect to y. And as expected, we had the exact same plot. All right, so that actually brings us to the end of this Python programming project. Very valuable, I hope, in intuitively understanding the gradient. If you so desire, please go back and change this function. It's not hard to do. You could make it whatever you wanted. So back here, maybe instead of x times y, we have x plus y squared plus 10, something like that. Let's make this 2 times y squared. And we can go back and just recalculate these and plot our new graph and see how that changes our gradient. So here's this, and then if we get one more in here, we should have this, and there, in fact, we do. So here we have a different gradient. Since we're just increasing in the y direction, getting slightly larger on the x, this is the new gradient for our new function. So please play around with the function. This title is now wrong. And gain an understanding of how the gradient changes and how it always points in the direction of maximum increase for whatever equation that you're calculating. Also in this project, we covered the mesh grid. Mesh grid's a valuable Python programming skill to learn, since it's useful whenever we want to plot a function over an array of values. So I hope you learned a lot from this project, and we'll move on in our lectures to convex optimization.